So presumably up to this point, you've become very accustomed to the atomic structure, the quantum mechanical model, and you know the basics of bonding, covalent, ionic, and metallic. And you're now ready to look at the geometry of molecular substances and polyatomic ions. In this segment, we're going to take a look at the reason for looking at molecular shapes and what they aid in our understanding of the chemistry, and then we'll look at a convention that we use for predicting the shapes of molecules. The first thing we want to do is kind of give ourselves a rationale for wanting to know the shapes of the molecules. Well, those macroscopic properties, those things that we see happening to substances in our daily lives, are due to the shapes of the molecules. Here we have a polar bear that's sitting on top of, part of an ice cap here, some kind of an iceberg. And the reason he's able to do this is because that ice floats on water. Now, this is a very unique property of water. Most substances in the solid state, they're going to be more dense than liquid state, and so they would sink. However, because of the structure of water, water having a bent structure, it has this particular property. If water were to be linear, like this, our water molecule, remember, is an oxygen with two hydrogens on it. Okay. If it were to be linear in nature, this property would not exist. Okay. Because it has this bent structure, when water forms a solid, the molecules come together in such a way that they form these empty spaces in between the molecules. This allows the water then to be less dense or occupy more space in the solid state, and making it therefore less dense than the liquid state. There are 5 primary shapes to the molecules. I'm going to go through and just draw each of these real quickly for you. So we would have a linear type of arrangement. We could have a trigonal planar type of arrangement. So let me draw this over here. We could have something that reflects it's called a tetrahedral arrangement, where we would, and I'm going to try and draw this into some kind of a perspective for you, where we have one that's going back into the board, into the plane of the paper. The dashed lines are in the plane of the paper, and then one atom that is coming out of the plane of the paper. And then we could have what's called a trigonal bipyramidal, where we would have these 3 positions that are in the plane of the paper, one going back into the paper, and one coming out of the paper. And so these 3 right here are in the plane, with the other 2 on the top and the bottom. And finally, we could have what's called an octahedral type of shape, where we have 4 that we can imagine in the plane of the paper, one going back into the paper directly behind the central atom, and one coming straight out of the paper from the central atom. Okay. So these would be the 5 basic structures. Now, fortunately for you, I have another picture of this, so that you can see what these look like from a professional sketch artist. Notice that these also give the bond angles here. The more detailed that we need to get in our analysis, the more interested we are in the exact angle and placement of those atoms. Most of these angles are pretty easy to rationalize given our kind of background in geometry. The one that might be a little bit tricky is the tetrahedral arrangement in the upper right-hand corner there. Now, these primary shapes can vary by what we place at each one of those positions. So for instance, here we have the tetrahedral. If we were to not put an atom at the top position in that tetrahedral shape, we would end up with a slight variation of that. That would look like this. And if we were to further not put an atom in the lower right-hand position there, we'd end up with kind of a molecule that looked bent, which is actually what we have for water. So a water molecule is of this type. So if I were going to draw the structure for water, the bent structure for water would look like that. Again, here are some professional types of drawings for these. Tetrahedral, that name given to the middle diagram, there was one place that didn't have an atom in it, would be trigonal pyramidal, and then we had the bent for water. So the next question would be, well, what determines the actual shape of the molecules? Well, what we need to do is we need to consider the number of electron domains that are around the central atom. So if we looked at an atom, for instance, and we were going to put 2 electron domains around it, 2 groupings of electrons, obviously those electrons being negative are going to repel each other. So if I were to put one grouping of electrons over here, right, so it would be a bunch of negative stuff over there. If I were to put the other one in, it's going to tend to get as far away from that one as possible and be over on the opposite side. So that would make a type of linear arrangement. If I were to go to 3 electron domains, so if I were to put the first one here, okay, you can imagine the other 2 are going to fill in spaces away from that. And again, with the repulsion, they're going to form some kind of a trigonal planar arrangement here. And so we can keep going with this, adding more and more electron domains, and looking at how the repulsion puts those together, or how they arrange themselves to minimize the amount of repulsion that is experienced. The way the method that we use to predict then the shape of the molecules is called the valence shell electron pair repulsion theory, where we try to minimize the repulsion by placing the electrons in the appropriate places. So here are the first 2, using balloons to kind of see what this looks like, and the tetrahedral that's down at the bottom here. Where we might get confused is thinking that in a tetrahedral, if you put 4 electron domains around it, you might be tempted to do something like this. Okay, but the problem there is that you're not considering this in 3-dimensional shape. In 3 dimensions, we're not going to have that type of structure. We're going to have a tetrahedral shape. So here again are the 2, 3, and 4 electron domains. Again, showing how they would orient themselves in space. If we continue on, we have 5, that trigonal bipyramidal shape that we showed at the beginning, and 6, the octahedral shape, again, that we saw at the beginning. And again, keeping in mind the bond angles that would exist here. The next consideration that we need to make is, how do we get from the electron domain geometry, which is based on how many electron domains there are, to the actual structure for the molecule? So this is where we go from those 5 primary shapes to kind of specialized shapes based on how the atoms are actually arranged. So up here we have the structure for ammonia, NH3, and you can see that the first thing we need to do in order to determine the number of electron domains is do a Lewis structure for the molecule. So that should have been part of your chapter on bonding, preliminary bonding structures, or bonding theories. From the Lewis structure, we're able to figure out how many electron domains there are. So we have 1 lone pair and 3 bonding pairs around the nitrogen. You need to keep in mind that the Double bonds count as a single electron domain. Triple bonds count as a single electron domain because they need to be, localized in the same space around an atom. So for nitrogen, we have 4 electron domains. And 4 electron domains is going to give us a preliminary structure of a tetrahedral. So this would be known as the electron domain geometry. Now, for the actual molecule, what we'd actually see if we saw this molecule, we wouldn't see those electrons that are on the top of the nitrogen. So if we were going to redraw this without that lone pair of electrons, we would have the molecular geometry in the final picture. What you might want to, obviously drawing the balls and stick there, if you were drawing this yourself on the paper, you would basically just draw the same thing you had in the picture here. This is exactly what we wanted here. Let's do our wedge dash structure. So our wedge dash structure, so we would have the hydrogen going back into the paper, this hydrogen coming out of the paper, and this hydrogen in the plane of the paper with the nitrogen. So how we would draw that. And again, here's the kind of the ball and stick model that we would see. So again, hopefully this demonstrates that difference between the electron domain geometry and the molecular geometry. Now, as we go through, the number of electron domains, as that increases, we can get more and more complex structures. Mostly what we need to do is just kind of go through and practice these things. So you'll do a number of practice problems, I'm sure, getting used to the different types of structures that you can end up with. So we'll just go through them very quickly here. With 4 electron domains, you have 3 options. You have the tetrahedral with no lone pairs, trigonal pyramidal with 1 lone pair, and bent with 2 lone pairs. And again, that's a structure for water. 5, we have trigonal bipyramidal with no lone pairs, a seesaw or irregular tetrahedral with 1 lone pair. With the 5 electron domains, we do have a kind of a unique situation that the lone pair on the trigonal or the trigonal bipyramidal, when we have 5 electron domains, the lone pairs need to go on the equatorial positions, which would be that one and this one and that one. The 3 that are in the plane that's perpendicular to the paper in this diagram, you would fill in those places first before you put it into the axial positions. So you can see that in the next one here. This is with 2 electron domains, you get a T shape, and 3 electron domains, you would have linear. If we go to 6 electron domains, our tetrahedral, obviously with no lone pairs around the central atom, you would have an octahedral, so each position is occupied by an atom. 1 lone pair, it would go, actually it doesn't matter where it would go, but if you turn the molecule, you would see that you would have a square pyramidal type structure. And in the bottom one, you see what happens if you have 6 electron domains, but 2 of them are lone pairs. The lone pairs are going to tend to need more space, and so they're going to orient themselves on opposite sides of each other and form a square planar type of structure. So just to do a kind of an overview again here, the structure of the molecule is going to help us understand those macroscopic properties that we observe and explain those properties. To get to that molecular structure, we need to start with the formula for the compound, do a Lewis dot diagram, determine the number of valence electrons, use the number of, determine the number of electron domains, use the electron domains to come up with a preliminary or an electron domain geometry, and then use the electron domain geometry to finally come up with the overall molecular geometry for that substance.